My name is Michalina, and today I'll be presenting our work on detecting VPN traffic through encapsulated TCP behavior. For online users in countries with heavy censorship, VPNs are commonly used to attempt to bypass censorship. And many VPN providers specifically market their ability to defeat or bypass censorship and unblock websites. But as more users have turned to these VPNs to bypass censorship, governments and other actors who want to remain in control of traffic in their jurisdiction have made an effort to block these VPNs. Some common techniques to block VPNs are blocking IP addresses and domains that are associated with VPN servers, blocking ports that common VPN protocols use by default, and then also using deep packet inspection to inspect the contents of packets to determine the type of traffic, and then block based on specific characteristics like packet headers. Then in response to this, VPN providers have tried to evade this VPN blocking by rotating the IP addresses that they use for VPN servers, using non-default ports, and obfuscating traffic in various ways, for example, using an XOR patch. But these techniques to evade detection are not robust, and even obfuscated VPN traffic has shown to be fairly straightforward to block using VPN protocol fingerprinting. And on top of that, more recent work found a protocol-agnostic way to fingerprint obfuscated proxy traffic using encapsulated TLS handshakes. And encapsulated TLS handshakes refer to TLS handshakes that occur within an encrypted cover protocol. And in our work, we're expanding on this idea of detecting encapsulated features to distinguish VPN from non-VPN traffic. But instead of looking at encapsulated TLS handshakes, we look at encapsulated TCP features in general. Specifically, our work explores whether the RFC-defined characteristics of TCP leak that a UDP connection is being used to tunnel TCP traffic. To briefly show the intuition behind our approach, TCP has certain behavioral characteristics as defined by the RFC. So we have things like connection setup, slow start, acknowledgement packets, exponential backoff, connection teardown, all of these different things. So if an external network observer is looking at a UDP flow, can they use these RFC-defined TCP characteristics to determine, are they looking at a plain UDP flow, or are they actually looking at a UDP flow that's tunneling TCP traffic, which is then likely to be indicative of VPN usage? There's three key advantages of this approach. The first is that it relies on a fundamental feature of VPNs, which is encapsulation, and so therefore we don't need to fingerprint or account for specific VPN providers or protocols. The second is that the use of RFC-defined characteristics of TCP avoids any biases that might be present in particular data sets used to train ML-based VPN detection systems. And then the third is that many TCP behaviors are easily recognizable even when the packet payloads are encrypted, which means this is simple to implement. And this is important particularly because in practice, prior work has found that even advanced censorship systems like the Great Firewall use crude but efficient heuristics like protocol fingerprints, the fraction of bits set, and the position of ASCII characters rather than more complex methods of detection like machine learning. And although there are many requirements of TCP, we chose to focus on three requirements that are very easy to estimate compliance with, using only size, direction, and timing of packets. The first requirement we look at is the opening connection with a three-way handshake. And then the next two requirements we look at are both requirements of acknowledgement packets. The first is that an acknowledgement packet has to be sent back within 500 milliseconds of receiving data. And then the second is that the acknowledgement packet should be sent back after receiving 2 times RMSS bytes of data, where RMSS is just the maximum segment size specified by the TCP receiving endpoint. And obviously when an external network observer is looking at a TCP over UDP flow, they don't have access to all of this internal TCP information like sequence numbers or flags. So we're just estimating compliance with these requirements using heuristics based on size, timing, and direction. And more details are in the paper about the exact heuristics, but they're simple. And with these heuristics, we build a rule-based classifier to distinguish VPN from non-VPN traffic. And to summarize what the classifier does, to classify a given UDP connection as VPN, we require 1, the presence of an encapsulated three-way handshake, and then 2, a rate of compliance with our encapsulated ACK packet features of at least T, where T is a tunable threshold. And for evaluation, we only look at the first 100 packets, which is similar to prior work. To evaluate our methodology, we created a VPN, non-VPN dataset, and we collected almost 30,000 real-world UDP connections from our campus network, and then we generated 30,000 TCP over UDP VPN connections across 3 different traffic categories. We had web browsing, file transfer, and remote access. And the web browsing traffic was multiplexed, meaning that it could contain multiple underlying streams within the one UDP connection, but this is representative of real-world web browsing traffic and is also useful in evaluating the efficacy of the classifier to some amount of connection multiplexing. And for the VPN traffic, we connected to a VPN server managed by ExpressVPN and used the default OpenVPN UDP configuration. Here we have the results of both our classifier and the results of other VPN detection methods from prior work. I want to note that we don't use the same data set for evaluation as prior work, and even among the prior work, different data sets are used, so it's not a direct comparison. The portion of the graph that's shaded green is where the false positive rate is less than 0.6%, and this is the false positive rate of the inferred algorithm used by the Great Firewall as of 2023, so this provides some context for how effective the classifier is. And then to the right of the green shaded region, we see 3 machine learning based techniques, and because of the high false positive rate, these are likely not practical for a real world sensor. And then to the left, we have OpenVPN fingerprinting, which reports a lower false positive rate, but is specifically for VPNs that use this OpenVPN protocol. In the middle, we have the results from our TCP behavior classifier across 3 values of T, which represents the rate of compliance with our ACK packet heuristics. For SSH and file transfer traffic, the true positive rate was on par with other detection techniques, and the false positive rate was lower than the ML techniques. But the true positive rate for web browsing traffic was significantly lower. And remember that this web browsing traffic was multiplexed. So when we investigated this, we found that actually many of the 3-way handshakes were interrupted by DNS queries. So this shows that this normal amount of multiplexing does disrupt the handshake a significant amount of the time, and therefore limits our ability to detect this handshake. And because of this result, we investigated a few different modifications of our encapsulated handshake heuristic to understand how much can we adapt this heuristic to account for common VPN defense tactics like multiplexing or random padding without greatly increasing the false positive rate. We found that modifying the encapsulated handshake heuristic to account for multiplexing or random padding by themselves doesn't significantly increase the false positive rate, while increasing the true positive rate pretty significantly, especially for multiplexing. But then adapting the encapsulated handshake heuristic to account for both multiplexing and random padding, this does increase the false positive rate by an order of magnitude. So if both multiplexing and random padding are used, this would likely be enough to obscure the handshake from simple detection heuristics like ours. To give some understanding of which features were the most important for classifier performance, out of the 3 features, the encapsulated 3-way handshake was the most effective at distinguishing VPN versus non-VPN traffic, and on its own, it achieved a false positive rate of 0.33% versus, remember, with all 3 features, we had 0.11%. The 2 acknowledgement packet features were useful in negating false positives, and in our own evaluation, we had about a 67% reduction in our false positive rate, but neither of these heuristics would be sufficient on their own. But we would also note that these features do increase in their distinguishing power as you look at more packets, because there's more opportunities to see a missed ACK packet. So if a sensor was doing something like host-based analysis and looking at entire traffic flows over a period of time, these heuristics could be even more useful in comparison to an R evaluation when we're only looking at 100 packets. To summarize our work, our protocol-agnostic VPN non-VPN classifier achieved a false positive rate as low as 0.11% on production network traffic, and this is an order of magnitude lower than previous ML-based detection techniques, while also being much simpler. And most importantly, our work motivates that when we're building future VPN or proxy protocols, we need to actively consider how to mask the protocol characteristics of inner transport layer and application layer protocols. Thank you.